So, what we're going to do is discuss parallel RLC circuits. A parallel RLC circuit basically consists of a resistor, in this case a 1 k ohm resistor, C1, 0.68 microfarads, and L1, 100 millihenry inductor. So for this circuit, I already solved for the capacitive reactance and the inductive reactance based on these two components. And remember that the capacitive reactance is 1 over 2 pi f C, and inductive reactance is 2 pi f L. For the first step one, we want to do is solve for the current drops, that's I drops, or to say this is current drops. And remember, that's because for each one of these circuits, we're going to have IR1, IC1, and IL1. Remember, they're in a parallel circuit, the voltage is the same. So in this case, we're going to have 2 volts divided into 1 k ohm, and that's going to give us 2 milliamperes of current. IC1 is going to be, again, 2 volts, and remember, we should put the peaks right here, so we understand that we're in AC. 2 volts divided into 195.05 ohms, and that gives us 10.25 milliamperes of current. And last, for inductor, is 2 volts peak divided into 753.98 ohms, which gives us 2.65 milliamperes of current. Step 2 is to actually solve for the what we call the net equivalent of the circuit. In this case, since we're in a parallel circuit, we have to use the currents. And we know that the phasors that we have for this is I x sub c is going to point upward, and 180 degrees out of phase with that is going to be the current, I sub x sub L, which is going to be equal to 2.65 milliamperes. The net, what we call the net, I'm going to put it on this side right here, the net is going to be subtracting the larger current from the smaller current. In this case, since our capacitance current is larger than an inductance current, the phasor is going to be pointing upwards because its capacitance is a lot larger than the inductance. So this is going to be I sub x sub c net. I like to call it I sub x sub c net, or you could put down, another way to put this down is IC net. Both are the same way. Most people put it down as IC net. We'll keep it as IC net. Is going to be equal to, well, we're going to take the 10.25 milliamperes and we're going to minus the 2.65 milliamperes. And that's going to give us a total of 7.6 milliamperes of current. Step 3 actually requires us to redraw the circuit with our new, in this case, our new phasor that was our net phasor, which was C net, came out to be, with the current was 7.60 milliamperes of current. So what we want to do now is we're going to solve for not only the x sub c net, but we're also going to solve for the C net itself too. So this is what we call the equivalent circuit. In the equivalent circuit, we have our source voltage, which was 2 volts peak at 1.2 k hertz. We knew that the current for R1 was 2 milliamperes. This was based on our calculations from step 1. And then the current through the C net right here, which was solved by using the phasors and coming up with that subtraction of those two phasors, the current and the inductor. In this case, the circuit became capacitive, so we came up with 7.60 milliamperes. So the first thing we want to do is we're going to solve for we're going to solve for x sub c net. And x sub c net is going to be equal to, well, we just take the 2 volts peak and we divide it into the 7.60 milliamperes. And we're going to come up with 263.16 ohms for x sub c. Since we know that x sub c, this is the capacitive reactance for x sub c, we could solve for c, the value of c, which is our capacitor value, and that's going to be equal to 1 over 2 pi f x sub c net. And that was just using some algebra where I've used the equation 1 over 2 pi f c. So all I did was use some algebra and I came up with that equation right there. So in this case, what I have here is 1 over parentheses 2 pi times 1.2 k hertz times that by 263.16 ohms. In this case, we came up with a capacitor of 0.5039 microfarads. So that capacitor is 0.5039. So we solve those two. Step 4 is actually going to require us to find I total. And I total is going to be based on, because this is using some trigonometry as well as using the right triangle. Let me draw that out for you right over here. So basically we have what we have here is IR. This is I x sub c net. And here's our resultant, which is I total. This being a 90-degree triangle. This is our phase angle. So we can actually use Pythagorean theorem, and using some simple algebra, I total is equal to the square root SQR of the radical of IR1 squared plus I x sub c net squared. So in this case, we come up with, I didn't need to do that. That was the, I'm used to drawing things out like that, but sorry about that. So this is going to be equal to square root of 2 milliamperes squared plus 7.65 milliamperes squared. Therefore, I total is going to be equal to, so again, we take 2 milliamperes squared plus 7.60 milliamperes squared. I think I put a 5 there. It's supposed to be 0 because that's supposed to be this one. And we come up with I total of 7.856 milliamperes of current. So step 5 here requires us to solve for the phase angle. And the phase angle, theta, is equal to the arctangent. And since this is going to be, since this vector, we're using capacitance, the vector is pointing upward, not downward, it's going to be positive. Excuse me, the phasor, not vector, the phasor. So this is going to be I C net over I R net, IR. And what we come up with when we do that is, this is the arctangent of 7.60 milliamperes over 2 milliamperes. Since millis cancel, amps cancel, we're left just with a number. In this case, we are coming up with an angle of 75.2 degrees. Finally, in step 6, we can solve for the impedance of the circuit. Z total is equal to, again, voltage total over the current total. And sometimes people would say, well, can we do that before phasing? Yeah, you could do that before the phase angle. So we got 2 volts peak. Remember, keeping my units over I total is 7.856 milliamperes. And that's going to come up with impedance of 254.45 ohms. So the next part I want to talk to you about is what we call real power, apparent power, and reactive power. So real power, which is, we can solve it by taking P is equal to I squared R. Since this case, our R is our Z total, we can actually use this equation, which is the same thing. This is for AC, and this is for DC. We can say I squared times the impedance total. In this case, what we'll have is, so if we take our, since we already know I squared and our impedance of our circuit, we could take 7.60 milliamperes, square it, and times that by 254.45 ohms, which gives us 14.69 watts of power. So apparent power, that's the power that is apparently, quote, there. And the unit is VA, not watts, but volt amp. And the equation is voltage times the current. In this case, our voltage, because we're dealing with an AC signal, it's 2 volts peak, times that by our I, which is going to be 7.6 milliamperes of current. This gives us 15.2 VA for apparent power. Finally, a reactive power, which we call VAR, that's volt amp reactive, that's how we call this. That's equal to the voltage times the current times the sine of our phase angle. In this case, we got 2 volts peak, times it by 7.6 milliamperes, times that by the sine of 75.2 degrees. This is not a 0 right here, this is my pen making a mistake. That is equal to 14.6 VAR volt amp reactive. You notice that all 3 of these are very close together, are very close with each other here. So this is what we do when we're dealing with AC signals. We have real power, apparent power, reactive power. You'll hear these terms through when you look at equipment, different machinery. You'll see the VA on it. Mostly in transformers, you see the volt amp on it, and we call the VA. You'll see reactive power to it. And you may even see some real power to it. So I hope this gives you some information on how to take a parallel circuit and come up with the current drops, solving for the net reactance and the net equivalent circuit, solving for the phase angle, the I total, and then actually finally solving for the real power, apparent power, reactive power. The next step I'm going to do is build the same circuit on a different video, and I'm going to call it part 2. And we're going to see if our calculations actually measure up to what we measure using our test equipment. Thank you.